Okay, right now what we are trying to solve is a problem like this. So I just give you a specific instance this time. So we are trying to maximize an objective function, this time x plus y, meaning that the cx and cy is equal to 1, 1. So if there are no constraints, maximize x plus y. If I tell you this, you can give any arbitrary large values to x and arbitrary large values to y it's unbounded in this direction. So our optimization function has this direction, 1, 1. This is the 1, 1 vector. And if you continue increasing your x and y values in this direction, you continue increasing your objective function. Okay? So in order to bound this, we additionally add constraints such as x should be less than 1000, y should be less than or equal to 1000. Okay, these two here we say m is equal to 1000, and we add these additional two constraints, which is going to bound our, if this is the coordinate 1000, 1000. Okay, that corner of this blackboard, we are going to, so if this is 1000, 1000, we'll be, as we're increasing in this direction, we are going to, x plus y is going to be maximum at this point, 1000, 1000. Okay, so if you don't have any constraints, the solution of this problem is 1000, 1000. Now, each of the half planes, this is the solution that I'm going to propose. We are going to add each half plane incrementally. So this is an incremental solution, one by one. And the algorithm is this. The half plane that I'm inserting, incrementally adding to my solution, if the current, I'm going to maintain a current vertex, this is going to be V0, and as my iterations, and I'm going to indicate iteration I with this index I, at iteration I, this is V0, okay, so at iteration I, sometimes I will need to update this vertex, and sometimes this vertex is going to stay the same. Look at this case. If this was the vertex, this was the intersection at Ci. So I'm going to also denote this term, Ci is going to denote the feasible region by considering the first I half planes. Okay, C is the feasible region after I consider all the half planes, and this is the set of half planes. Hi denotes the set of first I half planes, and Ci denotes the feasible region determined by the first I half planes. Initially, C0 is this rectangular wedge, which is unbounded in one region, bounded at that direction. So initially, it's like looks like a rectangle bounded by two lines, but two lines of this rectangle is missing, unbounded. So initially, my feasible region C0 is this. Now, at one point, and Vi is going to denote the vertex at iteration I. So the current vertex I have found, which maximizes the objective function and which satisfies all the constraints up to the ith half plane. Now, let's consider what will happen if I add a new half plane. If this half plane is like this, and it's in this region is the feasible region The upper part is the feasible region of this half plane hi plus 1. Okay, the I plus 1 I plus 1 constraint may define, and I'm going to, this line, I'm going to name it as Li plus 1, the bounding line of this half plane hi plus 1. So half plane hi plus 1 is actually the whole region here, unbounded region, and this Li plus 1 is the line that bounds this half plane here. Now, if Vi is included in this half plane hi plus 1, what happens? Nothing changes. The intersection is going to be, again, since we are doing intersection, this convex region is going to stay the same, and Vi is going to continue to be the extreme point of this objective function. So if such a case happens, in our algorithm, we don't do anything. So that's a good thing. If all we need to do is, in our algorithm is going to have two cases. If Vi is equal to hi plus 1, then the next Vi plus 1, if this is the case, Vi plus 1 is equal to Vi. If not, if, for example, this Vi is not an element of this half plane hi plus 1. How can this happen? For example, if you move this half plane, this bounding line up, and imagine you moved it up, and this is the bounding line, for example. Now this becomes the bounding line of this half plane, Li plus 1, and my hi plus 1 lies here, this part. Okay, so the intersection of this is going to, this region is no longer going to be feasible. My convex region is going to end something here, and Vi plus 1, where is it going to be? So it's slightly going down. So Vi plus 1 is going to be here. And at that time, in that case, I need to, so it's the smallest, if again, I'm assuming my objective function is in this direction, okay? And assuming that there are no horizontal bounding lines, there are no horizontal bounding lines, you'll be able to uniquely identify this vertex. If there's a horizontal line, you are going to pick the one which has smallest x-coordinate. We also found a solution to solve this problem, to uniquely identify Vi plus 1. But what happens is that the new Vi plus 1, for example, can it be here? No, because it's not an extreme point in this convex region. So what we see here is that the new Vi, so the next question is, we are going to update this Vi, but how are we going to find Vi plus 1? How can we find new Vi plus? So how can we find this point here? We see that this Vi plus 1 is actually on this line, which is bounding the newly inserted half plane. So it's always, if Vi is not an element of hi plus 1, we are going to show that, there's actually proof in the book, which shows that Vi plus 1 is on the line that bounds this half plane hi plus 1. Okay, because it's like this half plane, if this is not a member, this half plane intersects our existing feasible region, and it actually decreases. It decreases our current feasible region. It's going to decrease, it's going to shrink our feasible region. And as it shrinks, this new boundary is going to be a boundary in this shrink region. And the extreme point in this, because it is the line that shrinks it, so the extreme point is going to lie on this line segment Li plus 1. And then the proof is by contradiction. Imagine if Vi plus 1 was here, we can say that we can always increase the objective function by going downwards in that direction. So it cannot be anywhere on this, inside this existing feasible region. You can show that it cannot be inside this region. It has to be on this boundary bounded by Li plus 1 by proof by contradiction. Because as you move along the line, for example, as you move along this line, you are always increasing the objective function, so it cannot be contained inside this feasible region. It contradicts with the definition of maximizing objective function. Now, after we find that it is on this line, the next thing is there an efficient way to find this Vi plus 1? How can we find this Vi plus 1, which is going to be the, we know that it's on this line, but how do we know whether it's this point or it's not this point, not this point? So how do we, it's like we need to do an intersection of this line with the current convex region, right? But wait a minute, we are not maintaining the current convex region. We are just maintaining the vertex, okay? On our algorithm, we are not doing, because if we do that, if we maintain the current convex feasible region, then we cannot do better than O(n log n), because the algorithm that was finding the feasible region at the end was in running O(n log n time. I mean, if imagine you come to the last iteration, and in the last iteration you want to do a line intersection with this convex region, so you have to maintain the convex region, and finding this convex region takes n log n time. So this is not what we want to do. We don't want to keep track of the current, we don't want to keep track of CI. This is, in other words, formula. We don't want to keep track of CI. So without knowing CI, how can you find this point Vi plus 1? And it's going to be, it's going to turn out to be an easy problem. It's like this. Since we know it is, because it's going to be easy, because we know something. We know that this Vi plus 1 on this line is on this line, on Li plus 1. It's not in an arbitrary region. I mean, it's on this line. So if it's, imagine this is Li plus 1. So it is somewhere on this line. But where is it? Instead of maintaining the current convex region, by looking at all the HIs, starting from H1, H2, H1, H2, all the way to HI. So these are the previous half planes that were inserted. So each of these half planes intersect with this, some of them intersect with this Li plus 1, some of them do not intersect with this Li plus 1. But what they do is, if you consider an intermediate HK, consider an intermediate HK. Without maintaining the feasible region, all I need to know is where this HK intersect this line. So it's just line intersection, okay? I mean, you can find this point. It's easy to find the intersection of these two line segments by going over, since you know all of your constraints, by going over, in order to find this Vi plus 1, by going over all your previous constraints again one by one, you can find their intersection with this new line. And if this intersection, if this says that, if this is the line, and based on whether this line bounds it on the left or on the right. For example, if this is the feasible region, now this traced part is the feasible region of this half plane. Then what does it tell us? This Vi plus 1 has to be on the right hand side, right? I mean, if these two lines intersect, and if this line was bounding this half plane on the right, then my Vi plus 1 has to be to the left of this intersection point. So is this clear? I mean, each of these, what will happen is that if I find all the intersection, all x coordinates, if I find the x coordinates of all the, here, an important thing I missed actually is that I showed you here this Li plus 1 as a horizontal line. What will happen if it's not horizontal? Even if it's not vertical, okay, if it's vertical, I can do something else. I can provide a different solution. But assuming that this Li plus 1 is not a vertical line, I can, even if it's like this, for example, I can parameterize the points on this line by their x-coordinate. What does it mean? Parameterizing these points by their x-coordinate, what does it mean? It means that if you give me an x-coordinate, I can uniquely identify a point on this line. So you don't need their x, since this is Li plus 1, it's a line. If you give me an x-coordinate, I can find you the corresponding y-coordinate of that point, the y-coordinate of that point. So all the points can be uniquely identified, all the points on this line can be uniquely identified by their x-coordinates. Now, if I have such a line, and if I know the intersection of this line with all the previous linear constraints, all I need to do is, if this linear constraint is bounding on the right, I'm going to take, so it's like, for example, look at this region. Where can Vi be, Vi plus 1 be? First, I need to tell you what is the feasible region of each of these lines. For example, if it's this region, okay, if it's this region for this one, and if it's this region for the other one, if these are the feasible regions for the other one, then what I have is an infeasible solution. This one says that Vi plus 1 has to be this way, and this one says that no, it has to be this way. If you intersect these two, the Vi plus 1 cannot be anywhere. So you may find something infeasible here. But what it turns out that the way to solve where Vi, now let's get back to this picture. This one is going to, all the lines that bound this on the right, for all the half planes for which their feasible region is on their left, I'm going to pick the minimum, the maximum of those, right? So let's see. This one says it has to be smaller than this. This one says it has to be smaller. So this one actually is better. So if it's bounding on the right, this one is going to, it has to be smaller than the minimum of these x coordinates that bounds on the left. And it's also, if something is bounding on the right, if it's saying that my feasible region is this region, it's going to be the x coordinate that I'm going to find has to be greater than maximum of such intersections. So all I need to do is, after this, I'm going to maintain a minimum and a maximum of these intersection x coordinates based on whether they're bounding from the left or bounding from the right. I'm going to maintain a minimum x and maximum x coordinate. And at the end, this min x max x, after I process all the half lines, it's going to tell me that your Vi plus 1 can be in this interval. If this interval is 0, it's empty, it means that it's infeasible. But at the end, it's going to give me an interval. And my solution, my Vi plus 1, is going to be either the minimum x on this interval or the maximum x on this interval based on your objective function. So it's at the end. And this, to find this, to find Vi plus 1, as you can see, we spent how much time? On time. So in linear time, we can find this. So by line intersection is constant time. In finding intersection of two lines is constant. And you are going to find the intersection of all the previous linear constraints with Li plus 1. You are going to find the intersection of L1 with Li plus 1, L2 with Li plus 1, L3 with Li plus 1. So, and you are going to do this I times. So actually it's not On, it's Oi. So in Oi time, you are going to find the intersection of all these previous lines with Li plus 1, and you are just going to use the x coordinate of this intersection, and this x coordinate is going to tell you whether it's going Vi plus 1's x can be greater than or larger than this value. You are during all these intersections, you are maintaining two numbers, the minimum x and the maximum x that it can, x value it can take. And initially, minimum x and maximum x is minus infinity plus infinity. After adding each of these lines, it's going to shrink. It's going to be maybe from minus infinity to 0, maybe plus infinity to 100. It's going to continue shrinking like this after, maybe for some half lines it may not shrink, it may stay the same, but it's again monotonically non-increasing. And at the end, after you process all the I lines, the final x interval that you are going to be left with is going to be the feasible region where Vi plus 1 can be. In other words, you're finding this. You are going to be finding this feasible region after these intersections. So it's a one-dimensional linear program, and it can be solved in OI time. And after you find this region, it's going to be either this point or this point, depending on what your objective function is. If your objective function is in this direction, it's going to be this. So you can actually check both points in both sides of the interval and pick the maximum or minimum of that depending on your objective function. Question?
We'll do this again and again.
Exactly. Very good. We'll do, so what it becomes? ON square. So now, we are going to do this. We do this for Li plus 1. We do this for Li plus 2, Li plus 2. So at each, so our algorithm looks like this. Starting from the first line segment, if we have an if in our algorithm, if Vi is included in Hi plus 1, do nothing. If it's not included in Hi plus 1, find this Vi plus using this algorithm. So it's like this. At each step of the algorithm, we either spent O1 time or OI time. And in the worst case, I can show you an arrangement of half planes which guarantees, I mean, you can easily find an arrangement of half linear constraints which guarantees you to update Vi at every iteration. So there are cases in which you are going to spend this much time, OI time, at every iteration. So it's going to take n squared time. So unfortunately, this algorithm says, okay, you had an n log n algorithm which maintains the convex region. Now you're looking for a single point, but it's ON squared time. So it's even worse. So why do we choose this algorithm? We are going to see the reason in a second. Although the worst case complexity of this is ON squared, we are going to see that most of the time, Vi is going to belong to Hi plus 1. Actually, the probability that this doesn't belong to Hi plus 1 is going to be 2 over I. It's going to be very small. And this will lead to the fact that the algorithm actually spends most of the time the algorithm is doing nothing. When you add new constraints, the extreme region is already included in the new constraint. So here's like this. Let me show you the worst case first. And it leads to a randomized algorithm at the end. I mean, it's randomized, but any random is good for this algorithm. So you don't need to even, you can just start with an arbitrary set of linear equations. It doesn't matter. So here's the worst case. Imagine this is my feasible region initially. Okay, I'm just numbering. This is H1. Sorry, actually these are the lines. So H1 is to the right of this line. And this is line 2. And line 3, line 4, line 5, and goes like this. So in this example, as you can see, the first Vi, V1 is, let's start with V2. V2 is here. And each time I add a new line, and their feasible region is always up. Okay, their feasible regions are up. So each time I'm adding a new constraint, I'm updating. So VI was initially this, then it's going to be this, then this, then this. So if all your constraints are ordered like this, this is going to take at the end O(n) squared time. Okay, in other words, I is equal to 0, 1 to n. Okay, which is equal to O(n) squared. Now, if my linear constraints were arranged like this, initially, you are going to have you need to spend O(n) squared time to solve this problem. Now, we are going to show that. So so this is the worst case. Let's try to analyze the average case complex. So we have an if condition there. Okay, that if condition says that if this occurs, you spend O(1) time, and if this occurs, you spend O(n) time. So what is the expected? What is the expected complexity of this algorithm? In order to do that, in order to analyze the expected complexity, we need to use some probability. Let's define a random variable, xi, which shows this random variable shows whether vi is an element of hi plus 1 or not. Okay, so this random variable, if vi belongs to hi plus 1, this random variable is 0. So it's a discrete random variable. It's either 0 or 1. Okay, so it's a discrete random variable. If vi belongs to hi plus 1, it's 0. If it doesn't belong to hi plus 1, it's 1. So our expected complexity is going to be the expected value of this summation. I is equal to 1 to n OI times xi. Okay. I mean, O1 I treat it as 0. It has 0 to our complexity. Actually, I need to do it. Maybe, yeah, we need to add plus 1 here, plus O1. It's not plus, actually, it's a choice, but I mean, yeah, we can actually add, yeah, no, we can do this. We can say if it's 0, it's going to be O1. If it's 1, this is going to subsume the other one, so it's safe to write this. Okay, now this, because of using the linearity of expectation, meaning that, so these are, as you can see, these are linear additions. They are linear, they are added, O0, O1, O2, O3, they are added like this. So the expected value of the whole thing actually can be written as this I is equal to 1 to n, OI, the expected value of xi. So what is the expected value of, so the expected value, we use this notation, again here. So the linearity of expectation means that if the expected value of a sum of random variables is equal to the sum of the expected values of individual random variables. Okay, so this is the linearity of expectation in probability theory. So here, what it turns out is that what is the expected value of xi? Is xi 0 or 1? And actually, the expected value of xi is exactly equal to the probability of vi not belonging to hi plus 1. Okay, I mean, it's going to be the expected value of this one is going to be a floating point number. Although this is 0 or 1, it's discrete. The expected value of exi is exactly the probability of vi not belonging to hi plus 1. So what is this probability? What is the probability that vi does not belong to hi plus 1? And we find this probability by what is called using backward analysis. We are going to assume everything is processed. We have processed ln. Okay, we are in this backward analysis. We are going to assume we are going to start from backwards. We have processed everything. All the lines are processed. And what will happen when we remove this one from the final solution? What happens? Now we are going backwards. We are not adding lines. We are removing lines in this proof. And we are going to see what happens when we remove this line. Whether Vn changes, when Vn changes or not. If, when we remove this line, imagine we have the final convex feasible region, okay? The final convex feasible region. If, when you remove one of the edges of this convex region, if the extreme point Vn changes only if this removed edge was incident to that vertex. Okay, this is the only case that when you remove that line, it changes only if it was the line that was defining that. Okay, just ignore right now. Ignore the cases where multiple, if they intersect this at the same point, multiple. I mean, it may not change anyway, but this is not going to increase the probability. This is also going to, because at this point, when you remove this, Vi does not change. Okay, if more than two of the same lines intersect at the same point, when you remove one of them, the extreme point is still the same. It doesn't even change at that point. Now, the only case when you remove one of them, if your extreme point changes, it's the only way that it changes that this Ln is defining this Vn. The only case it can change is that when you remove it, if this Vn changes, if it goes to another point, the only case is that if this Ln is defining that vertex. And imagine, and you know that at the end, we have a convex region containing many vertices, possibly n vertices, if each of the intersections define a vertex of it. And the probability that Ln is defining this vertex is going to be equal to 2 over I. Okay, because there are two edges in our convex polygon of, we have a convex polygon with n vertices. The probability that any randomly selected vertex any selected random edge incident to that vertex, that probability is 2 over n, right? I mean, just imagine a convex polygon. Pick a random edge of this polygon, and you know a vertex, for example, vertex 1. What is the probability that this edge is incident to that vertex? Since each vertex has two incident edges, the probability is that, what is the probability that it's one of these two edges? It's going to be incident to that vertex only if the selected random edge is one of two edges that are incident to that vertex. And if you have n vertices, and if only two of them are incident to that vertex, the probability of the randomly selected edge being incident to that vertex is equal to 2 over n. Okay, that probability is going to be 2 over n, which is going to be equal to this expected value. So each time, and this probability, and if we do that, if we replace this with 2 over I, and this 2 over I, it shows that the probability that Vi is going to change is very low, and it depends on your current iteration. As your iterations get higher, for example, in the 100th iteration, the new boundary is going to be less and less likely. It's only 0.01 probability that it's going to change this vertex. As you initially, when you're in the beginning iterations, your vertex is more likely to change because they are defining your convex regions. Initially, there are only two of them. A new edit region is going to define a new vertex, a new edit region is going to define a new vertex. But as the iterations go in later iterations, that probability is going to decrease and decrease. And in the 100th iteration, for example, it's going to be only 0.02 probability that this new line is going to change the current vertex. So, and this is going to solve to ON. Okay, so this algorithm shows you that, I mean, this case is the worst case, but if you just pick a random permutation of these line segments, if you just get a random permutation of these linear constraints, the expected running time is linear. So if you implement this algorithm and you practically time it in practice, we are going to see that it's as fast as linear algorithms. Okay, so this is an interesting thing in algorithm analysis, I mean, which includes the probabilities, probability and statistics. So the expected, maybe you may not be familiar with such analysis. I mean, in average case complexity, best case or worst case complexity, now there's something new. What is the expected time complexity of this? To find the expected complexity, we need to use these probabilities. What is the probability you take this branch of the if condition and the other branch of the if condition? Yes?
Hocam şimdi aslında problem sparse graph, dense graph'taki gibi hani çok fazla kesişen line var, çok yok. O arada bir şey yapamıyoruz. Hani ilk kesen sizin dediğiniz gibi görüyorum ben de. Burada bunu yapmamızı sağlayan convexity özelliği mi? Yani
yes, yes, it's the convexity. Yeah, the convexity is really important here, and because it's a very good observation. Okay, by the way, the monotonically non-increasing property is very important. Since we get the intersection of all the things at the end, the convex region is going to get smaller and smaller and smaller, and the probability that any arbitrary line includes this small convex region is going to be high. That's the main reason. That's a very good observation. As the iterations go, the convex region is getting smaller and smaller and smaller, and the probability that a small region is included in half of the, I mean, we are talking here about one line here just has half of the whole space, okay? I mean, it contains half of the whole space. So what is the probability that this small region is contained fully in the half space? And half space is really large. I mean, it's unbounded, but it's the probability that a certain convex polygon is contained in this half space is going to get increase and increase as your convex polygon decreases. So this is a very good observation. So intuitively, this is how you can explain this. So it's the randomized version of this algorithm is just, and the thing is, this analysis tells us that there is no bad permutation. I mean, this is a bad permutation, but you'll be really, to get such a permutation, you have to be really, really unlucky. The probability of having such an order to occur is maybe, I mean, 1 over all the possible permutations, which is very small. So just the final algorithm is just randomize these linear constraints, just pick a random permutation, and a random permutation of these linear constraints can be found in ON linear time. Or you don't need to do actually this pick a random permutation. Since just use the one initially given to you. Just use those faces in arbitrary order. But not to avoid some bias based on the positions of these faces, there may be some bias. The probability of getting such a constraint may not be too low if, for example, you construct your linear constraints based on the neighboring edges, and the neighboring edges are close to each other in terms of orientation, for example, in your mold. If in the mold, if you use neighboring edges and in that order in the linear constraint, that may have some bias on the, I mean, I don't know. I mean, this is just, I'm just thinking, this is not, for example, if these edges have similar orientations to each other, you may end up with an order like this. So what the randomized algorithm does is, if somebody gives you these linear constraints, just randomize them just shuffle those linear constraints, and any shuffling is going to give you a good ON expected time solution. So that's why it's called randomized incremental algorithms. We first start with some random, we have some randomness in the algorithm. Initially we randomize the linear constraints. Now, so this concludes the half plane, the mold pulling the object out of the mold problem. So in expected linear time, we can find out whether a specific top face allows us to pull the object out of the mold. But we need to do this for all the faces of the object. One face of the object may not provide a feasible solution. We need to try it for all the faces. So if the object has n faces, the total running time at the end is going to be O(n) squared, trying all the faces of the object, each time trying to find a solution. Is going to, so we can, in other words, the final conclusion here is that we can find whether an object with n faces can be is castable in O(n) squared time, expected time. Okay, so this is the final. So we reduce from n squared log n to n squared. So let's have a 10-minute break. Okay, a sharp time. We try to be on time. Okay. So and we are going to continue with the smallest and closing this problem. I'm going to shortly describe the algorithm, and we can start the new chapter, which is orthogonal range searching.